I think, to satisfy the objectives of this cost action is that our cases have to have information besides the technical information we need, of course. Something on, for example, what is the replacement value of a structure? This is necessary to know. What are the costs of structural health monitoring? How much does the campaign cost? Then what are the costs of maintenance and operation of the structure? And how does this operation and maintenance sequence look like? Then we go into non-availability. If we have a bridge, people cannot pass across the bridge, or they have, let's say, 20 minutes delay on passing the bridge. And if there are 200,000 vehicles, you can quickly imagine how many hours are lost. Other indirect consequential costs, we can maybe sideline them now, but if we go into this in depth, we will find out that this is important. Financing information we will need to consider in these life cycle engineering models. And then we have to know about the information on the use of the structure, the history and the future changes. You know, in civil engineering, the most monitored structures are bridges. Our bridges built 40 years ago have been designed to different codes, and they have a history. On one of our bridges on the Brenner Highway, which is 45 years old, we have a perfect record through the toll gate that the traffic has increased more than 500%. And the codes have changed considerably. We had 25-ton trucks. We now have 44-ton trucks. And 28% of the trucks, these are 16,000 per day, are overloaded. So the conditions change. What we want to know is, we want to know where are we. If this is our theoretically aging curve, and we make a monitoring, we might end up here. This means we find additional lifetime. And we can rate this. But this is not the subject here. We can go more complicated into a life cycle model. I just show it that what we want to achieve is that if there is an incident, for example, that then this life cycle changes, your capacity changes. If there's an earthquake later on, for example, you lose a lot. Then there is this recovery phase, resilience, nobody likes it, and then we find out what is our remaining lifetime. These are the questions our clients are asking us. They don't want to know how are we doing it, how do we assess condition, but they ask us, how much time do I have until I have to replace a bridge? And in practice, I can tell you that below 10 years, there is nothing. You need 8 years for the political process and 2 years to build a new bridge. Now a few cases of from very simple to very complex. This is an expressway in Australia, for example. It is across a valley where there is weak soil, and there is doubt that these piers might displace. So the next office of the surveyors are more than 1 day driving away. So to put a monitoring system, a very simple one, just a leveler, which communicates through satellite with the web interface, can be checked every day, and you can have an automatic warning on that. Very simple, very effective, very clear objective. If we go for buildings, this is in Dubai, the Gold Tower, 200 meters high. And you see some openings in the glass facade. 17 glass facades were falling down. And people wanted to know what was the problem. The problem is very often the ventilation stories. They have removed all the shear walls, more or less. And the building is now moving in 3 independent blocks, putting strain on the structures. With a simple system identification of the structure itself, and with this is one of these elements, the glass elements, you can find out that it is under strain because of this torsional movement. Very clear objective, easy to find how much does the monitoring cost and what is the effect, how much does it cost to stiffen the building to avoid this. Another case, stadia. There are a lot of stadia where you have very nice monitoring systems. This is the one in Vienna. a rather big one. A roof without support in here is only supported from the back, 305 meter diameter. It's also more than 40 years old, and the code has been changed a lot. Our Euro code now has increased the snow load, for example, by 100%. And the stability case here is the snow load. Not equally distributed, but when there is snow and wind, and the wind blows the snow into one corner. So a simple monitoring system with a frame of a camera. This is not yet big data, but big data could be if we have 100 cameras. It is automatically detecting the snow, including the height, and giving an alarm if we have this 40 centimeter in a certain corner exceeded. Again, a structure where it is easy to find out how monitoring can pay off quickly. This is this situation in two years ago where you see the snow accumulated on the roof. This year we had no snow at all. And the system generates automatically then the snow distribution and gives you an indication whether the load limit is reached or not. This is how it looks like, not so spectacular. Another very good field where there are isolated structures, we know them, is offshore. The setback is that these offshore people let you sign a 100-page agreement of non-disclosure, and therefore the best cases we have we cannot show. I can give a very quick show, but we cannot use as a test bed. Interesting is that this Met Ocean data, for example, in the North Sea have changed considerably. What you can see here is definitely not what this platform has been designed for. The wave height was 16 meters in 10 years ago. It's now 25.5 meters. So, and the difference is what you see here in this picture. Of course, we have sometimes less strong situations like this one, but we have these two types. This is a very interesting type because of we have so many, so we can use tools, just compare them. In a database, this is very excellent for a database, and we have the transformer platforms, which are interesting because of their size and of their construction type. There is this beautiful project in Germany, Alpha Ventus, where a lot of monitoring has been placed. I'm not aware whether this could be used as a case study, but there has been a lot of very interesting information has been gained and experience made. This could be discussed, or the construction stages, or the transformer platforms. Now, one case I can just show you the record we have done quite recently in monitoring campaign, system identification campaign of one of these structures. This is the record you see here. Here we have the frequencies and the amplitudes. You see two closely spaced frequencies here, and then the red line, this one corresponds to this peak. This is what the designer said, 0.44 hertz. The structure should have, and it has 0.13, 1/3 of what the designer said. The designer found that they are equally spaced or closely spaced, but the blue one corresponds to this one. These are extremes, which might not be the perfect case for application, but it shows with what kind of difficulties we will have to deal. This would be the first torsional, and these are the second ones. Actually, these are not corresponding to those, but it is a case where, let's say, the financial implication is in 8 digits, so very high impact. No. No, but you know, maybe many of you know the grouted joints problem. The grouted joints could also, well, completely fail. So this means that there is a gap instead of a joint. And then I'm happy that you didn't hear about it. please forget it. But these things are, standing on their piles. This is not a generator, it is a platform. And they are supported from the top, and they are swinging on the piles without checking. The jacket does not help. So very difficult, complicated process to repair. And you will read it in the newspapers 2 years from now, I guess. This was an interesting case which we could eventually use. We have also work in Iran. This is in the Caspian Sea. This is a semi-floater. These platforms are fixed by mooring lines. And in the North Sea, in the last 10 years, they have lost 180 mooring lines because of they don't know the tension properly and they don't know how to maneuver that. One mooring line costs minimum $1 million. So this is also a case where you have a huge impact if it fails, besides the fact that they, for example, cannot produce oil and gas at that time. Can be simple monitored like this with an accelerometer. This is the mooring chain here, and it goes on roll on top and roll on bottom, so you have a clear distance between 2 points, and you can quickly measure what is the load on this chain. It's 4 kilometers long, for example, in a 700-meter deep sea. Here we don't have this very strict confidentiality thing. This is how it looks in practice. And they were asking us for a calibration chart for this, where the mooring lines are driven. This is what it looks like. The red one is the measurement, and the black one is as it should have been. And so we can adjust. This can be done then by an Excel file. So it's working again. Then maybe one of the cases that might be used as a case study. This is from the IRIS project, S101. As I said already, bridges are the most or the best monitored structures in civil engineering. Here, availability is not the issue, but this bridge was destroyed. We were able to impose damage, artificial damage. We have done a lot of very nice measurements, and all the data are fully available. So if you need that, you can have the full data set, including description, including everything. This might be an issue. This is where the IRIS technology has been demonstrated, that you see damage, introduce damage. This was cutting the piers, cutting concrete, and this was damaging the post-tensioning cables. Very good documentation on that, available for everyone. There is nothing to hide on this. Another good case was this one. We have destroyed 11 bridges in the past 10 years, and we have damaged the post-tension cables, like this one. Then we demolished the bridge, looked at the cables, found the damage. This is 11 out of 18 strands broken, for example, and we're able to prove that the monitoring at the beginning was able to allocate this damage. A very recent case is the Izmit Bay Bridge in Turkey. I just returned yesterday from there. This is a suspension bridge, 1,550 meters span, the fourth longest in the world, after your Storbelt. And the catwalk collapsed due to a very unfortunate wind event. Here, the problem here was that the monitoring system installed didn't work because the wind was already on for 2 days, and the bridge was evacuated and they shut off the power. This is a problem we very often have. We have 8 hours of power supply, but it didn't help. You can see the damage here. These huge elements, this crack on a 35 millimeter steel plate, and the anchor here was completely pulled out by a resonance in the wake of this wind. The monitoring system could not have avoided it at all. And the situation here was very unfortunate because this was the most vulnerable time of construction. It's not more than a month where the catwalk is in this position. Later on, it is fixed and it is loaded. Then it does not help anymore. So here we just would have been interested to see why a 5-time over-designed anchor broke. So to see a resonance in reality would have been fine. The same was with the video cameras, didn't also work at that time. Only the tuned mass damper and the pylon worked, and we have a record of the tuned mass damper. Bad luck. There's another good case study. This is the US Bridge 202, not our 101. The US have double. So this is very interesting because almost the whole world participated there. And it is a very well or nice representation of do nothing. So maybe we should look at it in a little bit, let's say, comparative manner and say, well, okay, if you do nothing, where do you end up? Not only the bearings were stuck, there are more than 100 fatigue cracks, very professionally fixed. We did a nice study there on this life cycle. We put all the curves, we put all the methodologies, not the subject in here, but then predict life. And if you look here at this information, the main thing to know is how many years do we have of life of that bridge. You're applying European methodology, only 16 years left. So if you have a retrofit program small, then this means $920,000 investment. You add 3 years. Then medium, 1.1 million invested. You're 9 years, and so on. I think this is something that people would like to get from us. And our customers are not at all interested how we arrive at this point of time. How do we assess where are we on the aging curve? Or we could call it condition index, or we could go further and say this is a risk index. They want to know, I have so much budget, what can I earn from it? And the full program is then from 16 to 41 years. Another nice case where there is full information available is, we have a lot of heavy transports. There are bridges like this one. This is a single span bridge, 35 meters long, not very suitable for high loads. They wanted to transport 8 pieces which are between 260 and 305 tons across it. We made 5 measurement campaigns, one before, and then always 2 trucks per night, and tried to find out how does it work. So the individual pieces are shown here. It is going in the skew direction to hit all the main beams. And the objective was also very simple, to say, is there any damage after this load which goes far beyond the codes? And if you do a computer model, you're not able to show that this is safe. This is a kind of risk to do that, but here we have very nice data. We measure the deflections, we measure, of course, the dynamic response. And after that, we can say the structure has lost so much in capacity over time. This is what comes out. Again, very simple charts. This is what they are looking for. Another nice project which could be used, where we have the right to use the data, is the Haliç Bridge in Istanbul. As there will be the next workshop there, we can have a visit to this bridge. This is in the center of Istanbul. The metro is crossing here. This is Galata Bridge. Interesting structure, steel structure, of course. Cable-stayed bridge, a swing bridge on one side, 90-meter cantilever that opens to let the bigger ships pass. And we had an earthquake last year, 307 kilometers away. And we have a nice record of this earthquake. You see the normal train passages, and this is the earthquake. So this is considerably more visible than the train itself. So there's a full data set of 1 year available of this bridge. And this is the pylon sway, for example. A bad example is, again, in Turkey. This is the third Bosporus bridge. Here we have a seismic monitoring system in a 320-meter high pylon for a construction stage which is only 6 months long. So, you know, the probability of a big earthquake exactly in these 6 months is not so high, I would say. But a 320-meter freestanding pylon might have a wind problem, and the specification was asking for earthquake only. That's an interesting failure of investment for the supplier. It's not a failure, but for the people that want to use it. And another very interesting case where we also have the data is Halifax in Canada. There are 2 suspension bridges, very similar. One performs well, the other one does not perform well. The client wanted to know why. Is there a difference? Both of them were instrumented and operated for 2 years, and it was very clear that why the one works and the other one did not work. This is a look at the system. We even had a kind of damage signal in our campaign. You can see what you should also not see. This is water coming through the structures, through the expansion joints. There are some of the sensors here. We measure only the distance. Suspension bridges are swaying, and this measures the distance of the expansion joint. And we got clear outliers. Halifax is in the north. This water froze once and blocked the expansion. A very good example, also maybe a simple example, is Incheon Bridge in Korea. But it is a very good example because we have 5 years of records, uninterrupted records, which we don't have of any other project. In Europabrücke, we're measuring 17 years, but never uninterrupted. This is because we have installed an independent power supply with solar panels, because it's in the middle of the seas and nobody can steal that. So there's a lot of data available from that one. The main monitoring here is on expansion joint and bearings. Besides the dynamic characteristic, you see the weekly cycles, and here we get the accumulated or let's say the eaten up life of these elements. It's a good case for use. And finally, these data, for example, we can offer online for download. There's a button to download it into Excel. So this is something that can be easily handled by everybody. So in the end, let me just summarize my opinion. You know, besides teaching monitoring, I do a lot of consulting work, and this is more the practical issue. Now monitoring becomes more and more part of asset management. We work with ISO 55000 in asset management, and we use the ISO 31000, the risk management framework. We have currently drafted a new Euro code on risk-based inspection, which is already accepted and will come out. So we have tools that can use the clients, particular in, let's say, changing the frequency of their inspections. We do not have the same frequency of inspection at the beginning when a project is brand new and at the end when it is already aged. Then we need figures to demonstrate the impact on structures which are heavily used. The non-availability costs are X times higher than the costs of any repair or the cost of the bridge itself. So a good example has to have some relevance to that. These cases will help to prove the concept, as I hope so. I have no preference in any of these, and you don't have to select any of these. And I would be happy to receive within our group, or we would be happy to receive as many as we can, and we will make a good selection. And one might be also benchmark. Then BIM, Building Information Model, is perfect with monitoring. This goes together perfectly. We in our practice already use this for design of structures. So this should be also answered how this will go together, because the asset management people are also using this instrument to get their information. Availability and performance costs gain importance. As I've said this already, we cannot drop this. So thanks.